Good afternoon. How are you guys doing today? All right. Like I said, I'm here with Ping Golf. Give you a little background on the company. We're actually a small United States-based company, privately held corporation, although we are a global brand. We have a presence in a lot of different companies. I believe we have offices in 10 different countries, and we do business in over 70 different countries. And believe it or not, 50 years ago, this company actually started in somebody's garage. So a little background on our founder. His name is Karsten Solheim. He used to be an engineer for GE. And one day he got invited out golfing with some buddies, and he went out and he got very, very frustrated. Evidently, it's pretty hard to hit that little ball and make it go where you want to go. So he went home and used his engineering knowledge to build a better golf club, design something better, something that would work. And this is actually a sketch of the design. And it's where the name of the company came from. He moved the weight out so you can get better moment of inertia, better stable putter so that it would work better for him. And when you hit it, it was a tuning fork. It actually made a really crisp ping sound. And that's how we got the name of the company. So, picture him playing with Bob Hope. He was a great guy. He was very passionate about engineering, very passionate about golf, and very passionate about life. Great company to work for. So I'm here today to talk to you about how HPC and CAE tools are changing the game for us. It's really made a huge difference in our business, made a big impact. Saves a lot of time, as a lot of you know. When you can simulate things, it's a lot better than building them. Saves a lot of money. And because we're saving time and money, we have more resources that we could put into innovation. And that's providing us a very big competitive edge in this market. It's a fast-paced market. It keeps changing every year, and we have some big competitors to go up against. Something that a lot of people don't know, we're a privately held corporation, so we don't post our revenues, we don't post our sales, but 80% of our annual revenue is generated off of new products and new innovations. And without those innovations, we don't make money. So let's outline this. It's an age-old problem. A lot of people have seen it in one way or another. Let's make it more specific towards us. Our old product design cycle, this is how it was in 2001 before I started working there. If you wanted to make a prototype, you had to order it, and you had tooling costs associated with that. You know, for us, it was anywhere from $5,000 to $10,000 just to make the tools, to make the prototype. Then you're looking at lead times of 6 to 8 weeks. So we're sitting there twiddling our thumbs for 2 months, waiting for the prototypes to arrive. Then we have to qualify the prototypes. We have to test them. We have to test them for sound. We have to test them for performance. We have to test them for durability. And if something goes wrong, and it usually does, we have to go back to the drawing board, rinse, repeat, and by the time we're finally done with it, we could have wasted about a year in product development. Well, all that's changed now. Since we've implemented tools like Altair's HyperWorks solutions along with eCompute and our HPC platform, we've been able to speed all of this up. We do all of our prototypes virtually now. We can get through these prototype loops much faster. We also have the advantage of visualization. You know, before if something broke, we had our engineers round up the troops and kind of guess at what the problem was. Now it's a good guess, a bunch of smart guys, but at the end of the day, it's still a guess. With the visualization tools that we have here, we can isolate the problem, locate what it is, where it is, and figure out how we can fix it, and we can fix it quick. In fact, none of our engineers are allowed to order prototypes unless they have some kind of finite element result showing that it's a good design and they're not wasting the company's time and money. This is a picture of one of our main problems. It's a dynamic impact. There's a titanium plate. It weighs 200 grams. It's approximating what a titanium driver would do in this situation. And we're shooting a golf ball at it, excess of 100 miles an hour. And as you can see, that golf ball, you know, they don't look that flexible when you just put them on the ground and hit them. But let me tell you, at 100 plus miles an hour, it's just it's a crazy squish-squash ratio. It almost bends in half sometimes, depending on how fast you're hitting it. So we have to have some really advanced material models to handle all of this simulation. We're pushing the materials, the titanium, almost all the way up to its limit every single time we're hitting it. And the golf ball has some really interesting properties to it as well. It's actually the most difficult part of the entire equation. So we have a lot of custom material models. We have large deformation, high strain rates. There's no factor of safety that we have to work with. So like I said, we push the materials all the way up to the limit and sometimes over. Then there's that golf ball, that viscoelastic material model. And so we have to have full stress strain curves. We have to have shear and bulk moduluses, relaxation functions. It gets very technical, and we've spent a lot of time and money invested into modeling these things. Here's another shot of that golf ball just moving a little bit faster. And the test we were doing, it's called a coefficient of restitution. We shoot the golf ball in, it bounces back, we measure the velocity ratios, and it tells us how efficiently we're transferring energy into that golf ball. Well, the problem when the first time I tried to simulate it, I kept getting a COR of 0.99999. Well, because the computer, there's no friction, there's no gravity, there's no energy loss unless you put it in there. So we invested about 3 months and tens of thousands of dollars trying to figure out what's inside that golf ball and how it works mechanically when we simulate it. You know, it's no mystery that none of our competitors were willing to share that information with us. This is, I put this in for giggles. This is something that actually did happen to me. I was running a simulation one night, I was really tired, and I accidentally swapped materials 1 and 2 for 3 and 4. It happens, but so you've got a titanium golf ball moving at about 140 miles an hour into a golf club made entirely of rubber. But you know, the computer, it's a powerful, I didn't get any errors, nothing crashed, it continued to go just, you know, business as usual. You ask a computer a silly question, it will give you a silly answer. But you know, you really have to pay attention to the materials that you're putting in and all the information. Make sure that the information you have is valuable and you're putting it in there. That way you can get the best results out of it that you could possibly get. We've learned this over the years, and you know, I was embarrassed at this at first, but now it's just funny. So let's get into some products. I know that's what you guys want to see. Our flagship products are the titanium drivers. Everybody loves to hit the driver, make it go far. We do tons of simulations, again, on durability, sound, structure. Sometimes we have to figure out if we're going to put a weld on this part, where does the weld go? Where's the best position for it? And since we've been doing work like this, I've never had a failure at a weld in any of these products. And that's because we're able to simulate it and identify where's the best place to put it so that we're not damaging the structure every time we hit it. I love this view because you can really see it's a dynamic structure. It's not just the striking surface that's moving. I mean, everything is bending. That first third of the whole structure, you know, we get to see what's bending, how much it's bending, why it's bending, and what we can do to change it. And sometimes the difference between pass or fail in these tests is a couple thousandths of an inch of titanium in the wrong place. And using the HPC platforms allows us to get high-resolution images and high-resolution models to give us the best information possible to make these decisions. The most ridiculous problem we've ever run into, which is the next slide. A couple of years ago, the USGA changed the rules of golf, and there's a conformance limit on drivers. They actually can only be so good. And we ordered some prototypes, and they performed outrageous. Everything was great. Durability was awesome. But it didn't pass this USGA conformance limit. They were actually too good. We couldn't sell them to the public. And it's this test right here. There was a couple images just before this. They have a metal hammer, roughly the size of a golf ball, and they swing it into the golf club, and they measure the acceleration. They then run that through an algorithm, and it spits out a number. If that number is too high, it's non-conforming. You know, there's a lot of other race cars. There's limits on those, baseball bats. Well, golf clubs too. So we had to develop this simulation to figure out what we can do to modify either the structure or the materials or change something so that we can bring that number back into a conforming limit so that we can sell them. And this specific one, we were going to have to do a complete structural redesign. And I had an idea. I said, instead of changing the structural design, what if we went through a series of tests where we heat treated it virtually to see if we can heat treat this number back into conformance? So in one afternoon, we sat down and did a series of experiments, and we actually found a number that agreed that it was conforming, and we could actually change it. So we sent that information to the supplier, gave them a target modulus, and said, we need you to heat treat the part, hit these specs, and we fixed the problem in less than a week. But funny problem to have. Your product is too good for public consumption. Aerodynamics. We also do a lot of CFD. You wouldn't think so. I mean, you're only swinging about 100, 115 miles an hour, but the drag generated by that club head could actually slow down your club head velocity, and we want to make sure we're not doing anything to hurt the club head velocity. It's fun stuff, too. Irons, we do, every product that we manufacture, we actually do simulations on. We know exactly, like this one has a two-piece, it's a titanium face and a steel body, how thick to make the joints, the ledges, and where we're going to combine the two parts. This one here was made strictly for Japan, and it's two materials brazed together. We had to analyze how these two pieces work together, how they fit together, and where the braze joints should be. And start to finish, that product took less than 2 weeks to virtually prototype. And once we got the first prototypes in hand, they went straight to market. So we're really, really speeding up the ability to get these products through our virtual prototype loops, get them in, get them qualified, and get them out to market, out to the public. There's some fun videos in here for you too. You ever had that really bad shot and that shock wave came all the way up into your hands? This is what's happening. So everything we do virtually, the reason I put this in here is to show that we have robots that physically test everything we do virtually so that we can confirm one and the other. You know, we really have a correlation going on as to what's happening physically, what's happening virtually, how we tie the two together so that we can verify everything we're doing is accurate. Oops. We even do a lot of testing with our wedges. You ever see that tour player pop that nice shot, jumps up, hits the green, checks up, and rolls back? It's an amazing thing when you see it. Well, we do a lot of simulation to find out when we move the center of gravity around on that part, it changes the way it interacts with the golf ball and can increase or decrease the ability for that part to actually make that ball spin. So we do a lot of studies on where we want to place the CG and why and how it's going to affect the ball and how much spin is too much and how much isn't, not enough. Find that little sweet spot. But there are things we do to simulate all of that, and of course, we verify everything with testing. Let's see here. Oh, this is a fun one. We actually design and make all our own golf bags as well. And it's a fun project, and we had this one problem one year where the trunk of a car in Phoenix can get up to 200 degrees in the middle of summer. It's outrageous. And when you have a couple of golf bags in there, they put pressure on each other and they actually collapse the tops of the bags, because that plastic is very pliable at those temperatures. So we had to figure out a way to simulate that. And instead of putting a whole thermal cycle and a load, we decided to just test the materials at that temperature, get those material properties, and then just do a simple static loading at temperature. So, I mean, we started looking at the big picture and just started whittling it down until we got something really interesting where we just got better information about the material, and we were able to do turn this around in 45 minutes now. Somebody sends over a new bag top design, and just get right back to them after lunch. But everything we make, we simulate, we test, and we prototype. So how does this impact our company? This is a picture of our trophy room. Every time one of our golfers wins a major tournament, we'll make 2 golden putters. One of them goes to the golfer and the other one stays in the vault. And I can't even begin to tell you how much money is in that room. Some of them are plated depending on the tournament, but if it's a major tournament, it is solid gold. There's a couple of wedges in there. Some guys chipped a shot in, so they decided instead of a putter, that guy was going to get a wedge. Tiger Woods, when he was younger, he used to play for us. There's 3 Tiger Woods putters in that vault somewhere. Don't know where. I think they're on the left. But I can show you a little bit about engineering performance over the years using FEA, CAE tools along with the HPC platform. This is as long as I've been with the company. Started in 2001. And the green line represents the number of product families we've been able to launch and get to market every year since 2001, and there's been a steady climb. I mean, it's just outrageous how many products we're able to get through now that we can get through the process faster. And the red line shows the number of months it took to get to market. That was almost 2 years over there in 2001 it took to get through all of the prototypes, all of the iterations, make sure all of the products in the same family were ready to go. And we've had a steady decline since then. The amazing thing is we were able to do all of this without increasing our engineering staff. We're able to do that with the same number of engineers. So we've increased output. We've increased the resources we've been able to put towards R&D. And again, we've done that all without increasing staff. So I think that's it.